Okay, quiz number 13, and it's partial pressures and kinetic molecular theory. So for number 1, a mixture of gases contains 0.25 mole of helium, 0.75 mole of nitrogen. If the pressure is 760, what's the partial pressure of each one? Well, let's get some data here. Let's see. We got moles of helium, and that's 0.25. And moles of nitrogen, and that's 0.75. Well, I made it this way deliberately so it would give you a 1 for the sum total of the moles. The sum of the moles is, of course, 1.00. Then we calculate mole fraction. Mole fraction is 0.25 over 1, which is equal to 0.25. And that was for helium. And then we calculate the mole fraction for nitrogen, and that's 0.75 over 1, and that's 0.75. Well, if you have a mixture that gives a total pressure to equal 760 millimeters, then the partial pressure of each one is the mole fraction times that total pressure. So the individual pressure is equal to the mole fraction of whatever component you're working with times the total pressure. So in this case, we have pressure of helium to be 0.25 times 760 in millimeters, and that up a little bit. Nitrogen to be 0.75 times 760 in millimeters, and we'll get 190 and 570. And I got bravo choice on that one. Any questions? No. You will see this kind of question on the major exam. Be sure that you make a note of how it's approached. The difference one on major exam is I will not give you 0.2575 to add up to 1. Now, real quick. Okay, helium takes 30 seconds to infuse from a pressurized container. How long does it take hydrogen, molecular hydrogen, to effuse from the same container and the same pressures? Now, effusion, just to review, is the discharge of a gas if you make puncture a pressurized container. And we showed you that yesterday. Sealed, okay, and if you puncture, you'll have the gas spewing out as a function of the pressure, and it takes so much time. And we found that the effusion time, or the effusion velocity, is directly proportional to 1 over the mole weight. That is, the heavier the molecule, the slower it moves. The heavier the molecule, the greater time it takes to effuse. So in your studies, check mark those 2 points. Size governs the rate of effusion. Now, to be more specific, velocity on the square root of mole weight 1 equals velocity times the square root of mole weight 2. This is Graham's law. if we incorporate temperature into this equation, distance equals velocity times the time. So this is how this gets in here. Distance equals velocity times the time, and we need to substitute for velocity here, so we will solve for v, which is distance over time. Well, if you're comparing in these kind of problems, you're doing a comparative between two different gases, okay? So essentially both gases are going across the wall of the container at the same distance, so it is assumed that this v is a 1. That's where we can simplify the mathematics of the equation. And then 1 over t being v, we'll put it right in here, and we'll have the time equation for Graham's law. So essentially they were asking for how long does it take hydrogen to effuse. Well, it has helium. Helium has a formula weight of 4 atomic mass units, and it took 30 seconds to remove that one. H2 is 2 atomic mass units. Note the subscript. And I sometimes throw a curve. I might put neon down there. Neon is not diatomic, so just be sure you get the right molecule. Be sure to study the subscripts and stuff. Anyway, 2. And we have a time for effusion of helium. Hydrogen is 30 times the square root of 2 over the square root of 4. That's going to come out in seconds, and my calculation shows 21 seconds. Alpha choice. It's not a difficult problem. You just have to understand, and I think you do, that the heavier the particle, the slower it's going to move. Race cars versus large trucks, so to speak. And learn the equation, and you can recognize from the data. I'm not going to throw you any wild curves on this kind of problem. It's either going to be a calculate time, or calculate a velocity, or even calculate an unknown mole weight, given both velocities. This kind of thing. So it's going to be straightforward on this kind of problem. So now here's a problem on RMS velocity. Okay, we were talking about root mean square speeds here, and what's the root mean square speed? You'll see if you stay in statistical chemistry and start working with things like thermodynamic qualities and kinetic molecular, you'll see velocities and averages with little brackets around them. You'll see bars over them. Maybe you already know this. Or AVGs like that. So they'll come up in a variety of forms, but they still mean essentially the same thing. I use this little bracket thing. It's just habit. Where T is temperature, Kelvin, as you recall, and M is mole weight. And I just literally put atomic mass units. I don't put the units in here because I know the formula that I have is going to come out in meters per second as the velocity units. Now, if you have Ebbing's text in the 9th edition, you can go in there, and they use that RMS velocity as the square root of 3RT over moles like this, and they take the R value, 8.314 moles per, 8.314 joules per mole Kelvin, and convert joules to kilogram meter squared over second squared, and then they go through all this other. That's not usable, in my opinion. So just know that T over M times 158 give you meters per second. You got it made. But at any rate, we'll see the velocity to be 158 on the square root. What did I give you? 25 degrees Celsius is 298 Kelvin. 4 for, I did say helium, yeah. And the outcome of this is meters per second. And I get 1364 meters per second. Very simple, very straightforward. Don't make it complicated. I use this a lot in comparing how velocities change as the temperature changes, or I want to compare large particles against small particle gas phase, and most of it's just fooling around with the numbers and seeing what they look like. B choice. This next one is more in tune with the idea of the kinetic molecular theory in terms of particle. Okay, you're given a little bit of data. The root mean square speed of a gas expressed in meters per second is defined by the velocity equation, 158 square root of T over M in meters per second. And where T is in Kelvin, M is a formula weight. For any given substance in gas phase, which conclusion can be inferred from the expression? In science, it's very important that you be able to look at a math equation and kind of translate what the math equation is telling you. As you change one of the variables in it, so will that function, like velocity. So it's like, well, what will velocity do if I increase the temperature? Well, the way the equation's set up is directly proportional. Or what will velocity do if I increase mass? Well, now we've been barking that all morning. Increase mass, you decrease velocity. So that's an inverse relationship. So that's very important to consider, not just for this problem, but for any equation you study that deals with some physical variable that you're measuring. Okay, number 8 choice. Root mean square velocity is inversely proportional to mass and directly proportional to temperature. Well, yeah. So A is a yes. RMS velocity decreases with increasing mass and decreasing temperature. Decreases. Yes. So if we lower the temperature, velocity is going to go down. If we lower the mass, increase the mass, velocity is going to go down also. So B choice is a yes. And I did a little calculation for, let's see, what is the root mean square velocity? 158 on the square root. 100 grams per mole at 400 Kelvin, so it's really 400 over 100 meters per second, and this drops out to 2 times 158 meters per second. Whatever that comes out to be, 316 meters per second. So the answers all of the above are correct. That would be D choice. And finally, for number 5, I gave you some compounds, A, B, C, D. I gave you CO2, I gave SO2, ammonia, and hydrogen fluoride, and all of those are in the gas phase. And their formula weights are 44, 64, 17, and 20. Like that. So from the root mean square velocity equation, which one, or the Graham's law, which is velocity is proportional to 1 over the square root of mass. As you increase mass, what happens to velocity? It goes down. Okay. SO2 has the largest mass of the collection, and so I would have chosen B choice in that one.